Complementary slackness. In solving both the primal and dual LPs, one can use the simplex algorithm to solve the primal LP and get the dual solution from the simplex tableau. One may also use the dual simplex in order to get the optimal solutions for both the primal and dual. In this video, we will discuss a way to solve primal and dual LPs using the theorem of complementary slackness. This theorem relates the optimal solutions of the primal and dual LPs. This theorem will be useful in times when the optimal solution values of one of the LPs are already given and you are tasked to find the optimal solution of the other. In order to state the theorem of complementary slackness, let us first assume that we have a normal maximization LP as our primal and a normal minimization LP as its dual. Then, we have the theorem stated as follows. Remember, normal maximization LP means that all the constraints are in the less than or equal to form, while in a normal minimization problem, all the constraints are in the greater than or equal to form. Also, all variables must be non-negative. Let the following be a feasible primal solution, and y is equal to y1, y2, so on and so forth until y sub n be a feasible dual solution. Then x is primal optimal and y is dual optimal if and only if, number 1, si yi is equal to 0, such that I is equal to 1, 2, so on and so forth until m, and number 2, ejxj is equal to 0, such that j is equal to 1, 2, so on and so forth until n. Take note that si are the slack variables of the primal LP and ej are the excess variables of the dual LP. Equations 1 and 2 imply that if one of the two variables in each equation has a non-zero value, then the other must be 0. For example, if the first slack of the primal LP has a positive value, then the first dual variable must be 0. If the third primal variable has a non-zero value, then the excess variable of the dual must be 0. To make things easier to understand, the theorem of complementary slackness can be put into simpler terms. Number 1, every binding constraint in one LP has its corresponding variable that is basic in the other LP. And number 2, every non-binding constraint in one LP has its corresponding variable that is non-basic in the other LP. To better understand complementary slackness, let us apply it through an example. We are given the following maximization LP. Max z is equal to x1 plus x2 plus x3 plus x4 plus x5, such that x1 plus 3x2 plus 2x3 minus x4 plus 5x5 is less than or equal to 3. 2x1 plus x2 plus 3x4 plus x5 is less than or equal to 5. And negative x1 plus 3x2 plus x3 plus x4 plus 2x5 is less than or equal to 4, while all x's are greater than or equal to 0. At optimality, the values of the variables are as follows. Take note, you can check the optimal solution using methods that you have learned. Let x1 be equal to x2, be equal to x5, be equal to 0. x3 be equal to 7 over 3, and x4 be equal to 5 over 3. Find the complete dual solution of the LP, given that the third dual variable, y3, is equal to 1/5. In order to solve this problem, let us first construct the dual LP of the maximization problem. Min w is equal to 3y1 plus 5y2 plus 4y3, such that the following equations y1 plus 2y2 minus 2y3, 3y1 plus y2 plus 3y3, 2y1 plus y3, negative y1 plus 3y2 plus y3, 5y1 plus y2 plus 2y3 are all greater than or equal to 1. Let all the y's be greater than or equal to 0. Now, given that we have x3 is equal to 7 over 3 and x4 is equal to 5 over 3, we can say that from complementary slackness, that the third and fourth constraints of the dual LP are binding. Thus, 2y1 plus y3 is equal to 1 is the third constraint, and negative y1 plus 3y2 plus y3 is equal to 1 is the fourth constraint. we are given that y3 is equal to 1/5. Therefore, solving the third constraint, we will get 2y1 plus 1/5 is equal to 1. 2y1 is equal to 4/5, so that y1 is equal to 2/5. Now that we have the values for y1 and y3, we can solve for y2. Negative 2/5 plus 3y2 plus 1/5 is equal to 1, so that 3y2 is equal to 6/5. In conclusion, y2 is equal to 2/5. The optimal solution will not be complete without the optimal z or w value. Substituting our values to the objective function, we will get w is equal to 3y1 plus 5y2 plus 4y3. Substituting, we get w is equal to 3 times 2/5 plus 5 times 2/5 plus 4 times 1/5 is equal to 4. Note that you can also use the objective function of the primal LP. Therefore, the complete dual solution is w is equal to 4, y1 is equal to 2/5, y2 is equal to 2/5, and y3 is equal to 1/5. You may check whether the corresponding constraints of x1, x2, and x5 are non-binding by substituting the values of the dual variables.